Alrighty, mathematical expressions. An expression is a series of variables or literals, like 2 is a literal, combined with operators. And a single variable or a single literal is also considered an expression. But if you have more than one variable, they're going to be chained with operators somehow, like addition. That's a binary operator because it requires two operands. X and Y are the operands. The operator is addition. Now we have a multiplication here. Well, it requires two operands as well. Well, it looks like it's got more. I see all sorts of, well, the result of this is one operand, and then that is the other operand. All right, now what about this one? Well, he's got two operands as well. He's got that and the result of that. So each one of them has two operands. It's just that some of them get evaluated before the others in order to provide the operand for the next operator. These are also called operators. That's a stream insertion operator. Stream because it's putting this into the cout stream so that it'll display the border is. So in an expression with more than one operator, and I'm pretty sure that everybody in here knows PEMDAS, P-E-M-D-A-S, except that this one doesn't have an exponent, but P being parentheses, M and D being multiplication and division, A and S meaning addition and subtraction. So expressions are evaluated in this order. If there's a single minus sign followed by a number, it's treated as unary negation, which makes it negative. So like that. That's actually -2, but it's 2, which gets reversed with a unary negation operator. Now, that's almost silly to think about, but in terms of compiler writing, you have to handle that case, because that means something different than that. That's a binary operator, which is going to subtract this from the operand that comes before it. I guess we could pretend that there's an imaginary operand in front of it, a 0. But anyways, ignoring the unary negation operator, multiplication and division are then have processed, and then addition and subtraction. And as far as multiplication and division are concerned, modulus is also considered division because it just means remainder, the remainder of a division operation. Alrighty, so what happens first? Multiplication. 2 times 4 happens first. So 5 plus 8, 13. What happens first here? Grade school math guys, you know what happens first. Do you do the division first or the subtraction? You're right, division. And then here, what's going to happen first? Multiplication, right. So why is this important? Because you can have an expression that you cannot intuitively convert into code. If you have 2x plus y over 3, you can't just say, cout, arrow, arrow, 2x plus y divided by 3. Instead, you're going to have to take precedence into account, and you're going to have to do some grouping. Well, for one thing, there's no such thing as an implied multiplication. So we can't just put 2x there. That's got to be an asterisk there. So we would rewrite that as 2 star x. But then, that's not good enough because we need this to be clustered together. So we would put x plus y in parentheses. And it would not be a bad idea if we wanted our result to have fractions to make at least one of these be a floating point. What do I mean by that? 2 divided by 3, if they're both integers, does floor division and it rounds it down to just 2, or just 1, right? It's not 1.5 anymore, it's 1. And so it'd be just like this was processed like this, which would be wrong. So if we were going to express this, 2 times that divided by 3, unless we were okay with it being rounded down like that. You'd want to make at least one of these numbers, either the 2 or the 3, a floating point number, so that you could get a result that was accurate. So the parentheses can be used to override the order of operations. 2 plus 2 has to be done first, and then the 2 minus 2 has to happen first, and then the multiplication can happen. So that happens first, according to our rules of whatever was inside it. You know, it could be a complex expression. Then that happens, and then that happens, and we get that result. I'm skipping through this because it feels like maybe I lectured about it, and I'm absolutely sure you also did it in fundamentals. And it's also junior high math, I believe. So multiplication requires an operator. You can't just do LW, meaning length times width. Textbooks show it that way, but we have to have the asterisk. There is no exponentiation operator. So you can't just do S star star 2 like you can in Python. Instead, you have to use the POW function. To use the POW function, you may have to include the CMath library. # includes CMath. Your Mac users do. Your Windows users do not. I'd put it in there anyways, just to make the code cross-compilable on multiple platforms. What this means is take that to the power of that. If we were going to cube it, it would be POW S, 3. Am I taping? Yeah, yay me. Okay. And then parentheses may be needed to maintain order of operations. This, for example, you want all of this to be done. You want all of this to be done, and then and only then do you want the divide to happen. So you would express it like that. You would express it like that, and then you would do the division. When you mix apples with oranges, type conversion. That means if you have a floating point number and an integer point number, a floating point number and an integer number, can you use them interchangeably? Well, the results actually differ. I just kind of mentioned that. But if you have 3 divided by 2, if you say x is equal to 3 divided by 2, it doesn't matter how you declared x. You could do that. When this is done, x equals 1. It doesn't look like it should. It looks like x should be 1.5. If you did this, float y is equal to 2 divided by 3. When you're done with that, or when the computer's done with it, y is equal to 0. Not y is equal to 0.666. The reason why is because if both operands of the division are ints, then integer division, floor division happens.
What if you declare y as a float originally?
It is declared as a float. And it doesn't matter because this is well, you mean like in another statement, like float y, and then y is equal like that? Yeah, same behavior. And the reason why is the expressions are evaluated left-hand side first, and then assigned across the equal sign. And since these are both ints, it doesn't matter what y is. This is going to evaluate to an int. So both operands of division are ints, and the result is an int. If one or both is a float, the result is a float. What's going on really is that for binary operators, binary arithmetic operators, both operands have to be of the same type before the computer can do it. Does that mean you have to write it that way? No. It just means that the compiler will provide the conversion code. If I do this, y is equal to 2 divided by 3.0, like that, here's what the compiler does when it's figuring it out. Well, that's an int. That's a float. Oh no. This is a binary operand. These need to be of the same type. Well, am I going to convert this to an int? Well, conceivably I could, but the right thing to do is to convert that to a float. Right? You're going to convert from the less complex form to the more complex form rather than vice versa. So, when the compiler has written the code to do all that conversion, then and only then does the division happen. And since inside it, it has taken 2.0 and divided by 3.0, then at that point our result really will be something like that. So the compiler will provide conversion code on the fly when it needs to, and when the data type is not of the same type. And the rules of the conversion are that less accurate types are promoted to more accurate types. What does that mean? Well, longs can hold more than ints. Floats can hold larger values than longs. Doubles can hold larger values than float. Any floating point type can hold the larger values than any integer type. So that is the hierarchy. So if you mix an int and a float, then the int will be turned into a float in order to do the operation. If you mix an int and a long, then the int will be converted to long in order to do the operation. Now honestly, it seems like even if we don't understand that completely, we would just program and use it and happily go on our way, right? If I did this, long, LL is equal to 33.3, no, 33 like that, followed by an L. And then we had float F is equal to 3.4. And then we did C out F divided by LL. We don't really care what's getting converted to what, right? But what does happen is since LL and F are not of the same types, the data is coerced to be of the same type. Coercion never goes down. We would never take a double and try to fit it into a long, or a float and try to fit it into a long, because floats have decimal points, and by putting them into an integer, we would lose that decimal point. So instead, the opposite happens. Stuff gets promoted up the hierarchy, so the long gets converted into a float, and then the division happens, and the result would be a float. So operations are performed between operands of the same type. If they're not of the same type, C++ will convert one to be the type of the other. It can impact the results of calculations. Here's the hierarchy. I gave you some, but ints and then unsigned ints are a higher order than int. And then longs and then unsigned longs, well, really it's long. And then unsigned longs. And then there's floats, and then there's doubles, and then there's long doubles. And I think we established that a long double is just the same thing as a double in this language, just like a single long is the same thing as an int in the Windows platform. So type coercion is automatic conversion of an operand to another data type. It can be promoted or it can be demoted. Promotion is when it's fixing it for your operators, right? When I did this, promotion happens, not demotion. Demotion is when you are copying across the equal sign and it winds up being the wrong data type. If you do int I is equal to 3.4, well, 3.54 is a float or a double. It's a different data type than this. They're not a matched data type. They will be turned into the same data type. Well, I is declared as int. It's never going to change. So this will have to be converted into an int. It will be demoted, meaning that some precision will be lost. The 0.4 will be lost. In Python, you handled that like this. And I know I've typed these versions. That works in this language, or you can do it like that. That works as well. This is the preferred way. There's another way that's even more preferred, which we'll hit later on. That gives you control over the demotion, data demotion. It indicates that you know what you're doing, that it's acceptable for that data loss to happen. Now, in some languages, it will not do this conversion automatically. Data demotion never happens automatically. Java is one of those. If you put this, it'll declare it as a syntax error, and it will not even compile. C++ will compile it, and it'll just lose that 0.4. When this is done, I will equal 3. In Java, you would have to go ahead and cast it. You would have to put that there to get it to compile. promotion. All of a sudden that sounds odd. Yeah, okay. And then a couple more rules. All of these that are lesser to ints, a char is a single byte, whereas an int is a 4-byte data type. So chars will get promoted to ints. Shorts are 2-byte values. They get converted into ints. When operating on values of different data types, the lower one is promoted to the type of the higher one. But when you use the equal sign, the type of the expression on the right will be converted to the type of the variable on the left, regardless of whether it's a demotion or a promotion. And that's what I was showing here. It's okay if you do this, float f is equal to 3. Well, they're not of the same type, but whether it's promoted or demoted is dictated by what is on the left-hand side and what's on the right-hand side. And since the right-hand side is a float, the left-hand side is a float, then this will get converted into a float. So by the time we're done with this, f equals 3.0 via promotion. And this is all very different than Python, where in Python the type of the variable is determined by the declaration and no conversion happens like that. 3 is not converted into a float. It is an int, and so f becomes an integer to accept it. The variables change depending upon what kind of data you store. But C++ is a strongly typed language, a strictly typed language, where you declare your variables before you give them values, and then that variable can only accept data of that type. Did I copy these rules and put them in here? Yeah. Overflow and underflow. I think we've talked about this. Occurs when a value is too large or too small to fit into the data type. Have we talked about that? Did I show you the Pac-Man screen with if you hit level 256 on Pac-Man? Okay. All right, so you're playing Pac-Man. This doesn't show the lead up to it. But you're so good that you've gotten past 255 levels. When you hit level 256, this is what you see. All right, great. Yeah. You can't play past this level any further. Because, right, you might be able to eat all those dots, but you're not going to be able to eat that, and you're not going to be able to eat that. Well, why does it do that? Because the programmer allocated 1 byte to hold the level. And I still haven't sat there and given you all the lecture about bytes and bits. The largest value that 1 byte can hold is 255. Now, the programmer of Pac-Man never dreamed that anybody would be able to play long enough to get past 255 levels. So why put 2 bytes to hold that value when 1 would do? And so what happens is you get what's known as rollover or overflow. The value 256 is too large to fit into a single byte. And so it flips back to 0. And so now it's trying to draw level 0 and has no idea what level 0 is. It's a programming error and it can't cope with it. If there had been a little bit of extra code added to it so that when you hit 255 it wrapped around to level 1 rather than 0, then this wouldn't have happened. So that is an example of overflow in action. There are other old classic video games that do the same thing. Like Donkey Kong also has a, quote, kill screen. It's a maximum screen, which at least provides kind of a, so that you can't kill yourself playing the game, because some of the old games, you could play forever, and so people would play for like 5 days straight to try to, to prove how awesome they were. And Pac-Man, you can't. You can only play 255 levels, however that would take. So let's write a little program that demonstrates overflow when a number gets too large. And what we're going to do is we're going to write a loop. And the loop is just going to double the value over and over and over until it gets to be too large. And so we haven't talked much about loops, but we're going to go ahead and demonstrate one. So I'm going to make a new file, new project. Now, since a short holds less data than an int, it'll do overflow more quickly. So I'm going to demonstrate this with a short. But all variable types can do overflow. So file, new project, empty project, Lecture E, OK. And by the way, if somebody texted me a message over the weekend asking me to call them, I lost all my text messages. I did not call you. And I don't know who that was. I apologize for that. I need to figure that out. All right, so add new item. All right, lecture e.cpp. I'm going to put my boilerplate in there. I'll erase you. If you don't have boilerplate saved on your desktop already, I recommend you do so. Anyways, so we haven't used fstream yet, and we won't for several other chapters, so that seems kind of superfluous. But I like CMath being in there so that we can use the POW function. IOStream is absolutely essential, or else we wouldn't be able to use cout and CIN. And string is just really useful because pretty soon we're going to be letting the user type in names and things like that. All right, so let's declare a little variable, a short int called x. And we're going to give it the value of 1. And then we're going to double it. I don't know how many times we're going to double it. Let's double it 20 times. So I'm going to write a little loop while. Wait, I need a counter. So int counter is equal to 0. Or why not start it at 1? Int counter is equal to 1 while counter is less than or equal to 20. Close parentheses. Open brace. Let's see out x, arrow, arrow, ENDL. And then let's double x. X equals x times 2. And then let's add 1 to our counter. Counter plus plus. Not plus plus 1. Counter plus plus. Let's make that 10 rather than 20 so that the first time we run it, we don't see any overflow. All right. So I kept multiplying by 2. So it shows the results 1, 2, 4, 8, 16, 32, and so on. Like that. And after doubling it 10 times, it was equal to 512. Well, I'm going to double it 20 times. All right, it hit a certain value. And then the next number was too large to fit into the amount of memory that's allocated for a short int. And so we see it choke there. Right there. How many times did it get to double? Well, once, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 15th time it was doubled, it blew up. What do I mean it blew up? It flipped to being a negative number. And then after that, it was just completely messed up. The value of x became too large to fit into the 2 bytes that is the allocated memory for a short. What if we made it an unsigned short? Well, let's find out. I'm going to make this unsigned short. run it again. It got a little bit further, right? And the reason that works, which will make more sense when we talk about bits and bytes, is that an unsigned number gets to use that first bit of the numeric value, whereas for a signed number, it uses that bit to signify whether it's a not positive or a negative value. So an unsigned value gets us that one extra bit, which lets us hold values that are twice as large. So it was able to be doubled one more time. It didn't get garbaged at that point, but the next time it doubled, it was too large to hold in an unsigned short. And so we had data overflow at that point. And notice that it's not a system error. It doesn't crash the program. It's not a syntax error. It just happens. So it's up to you to worry about it if you need to. If you have a value that can be too large to store into a short and it's a problem, then don't make it a short. Make it an int. Or if the value can be too large to be stored into an int, make it a long. Underflow is just the same thing. The value becomes too negative. And no real reason to illustrate that. Alrighty. So the variable contains a value that is, quote, wrapped around, right? It went so far positive that it became negative, or it got so large that it was reset back to 0. Different systems may display a warning, an error, or an error message. It may stop the program, or it may continue execution using the incorrect value. And that's the behavior that we're going to see. Right, you Mac users are seeing that as well. Did you type it in and get the similar results? Yeah. The operating system didn't care. So it would be up to the programmer to figure out that it was going to happen. Typecasting. All right, they show a funky way of doing conversion. Remember when I said that you can convert to an int using this syntax? By doing int I is equal to, and then I said you could do this, or you could do, or you could do I is equal to int, this Python style. Well, the groovy C++ way of it is doing this: static underscore cast angle, and then the data type that we want to convert it to, and then close angle brace, and then parentheses 3.1, 3.4. Much more complex syntax. In practice, it does the same thing as the other two. But you can put a different keyword there. If you want to turn it into a double, then you would replace the word int with double. You want to cast it to be a char, a char, you can do that. Or a long, you would put long there. So casting, let's give their definition of it, is manual data type conversion equals data type conversion where the programmer specifies the format to be converted to. And I'm sure that's bad English. It's got too many passive tense and stuff like that, and dangling participles and whatever. So, useful to see the integer value of a char variable, of a char variable, like a capital C. And then we want to cast it to an int so we can find out what a C is represented as, because underneath it all, everything in the computer is just stored as a number. Right? There's no letters in a computer. If you pry open the memory, you're not going to see special circuitry for holding letters. Instead, all you see are the zeros and the ones, which represent numbers. And so even letters are stored as a series of numbers. So, let's do this. Let's add to our little program. Let's create a character. I'm just going to call it CH. I'm going to set it equal to an uppercase A. And I'm going to create an int. And I'm going to set I equal to the integer version of CH. Then I'm going to print it out. So cout, arrow, arrow, ch, arrow, arrow, quote, space, equals, space, end quote, arrow, arrow, I, arrow, arrow, ENDL.
You don't have to put a space between the INT and CH.
No. Yeah, I tend to space things out way too much to make it easier to read. You could remove almost all the spaces and it would still work. I hope it makes it easier to read. Could be it makes it more difficult. All right. And so when it ran, at the very bottom of it, it says that A equals 65. What if we change it to a B? Well, a B, if we go by the alphabet, is one more than an A, so it's going to equal 66. A C would be a 67. A D would be a 68. Well, what about a lowercase a? All right, a lowercase a equals 97. Now, where are these numbers coming from? There's like they're random. Are they being drawn out of a hat? And Vincent and Tu have already sat through this lecture. And those who had my fundamentals class, which I don't think is very many of you, have also sat through this lecture. What about a period? What is a period? I run it and it's equal to a 46. All righty, well, that means a period is less than an A. What if it's a space? Alrighty, I run it again. Alright, is a space is equal to a 30? Okay, what's happening is you probably have heard the term ASCII. If I go to ASCII-table.com, or I just type in ASCII space chart and hit enter, and hit the first result, you know, there has to be some way of converting the letters on your keyboard to numbers that can be sent down a wire or saved to disk, right? And so the decision to make an A a 65 is an arbitrary one. They could have made it anything. But you have to standardize on something. And so somebody came up with this standard, and it evolved over time. ASCII stands for American Standard Code for Information Interchange. And it became widely adopted by a lot of places, not just Americans. Everybody who speaks English wound up using ASCII. The Russians, I'm sure, had a different character set. And at that time, their computers did not need to be compatible. Pretty much all computers that you can find, except for strange things like old mainframes, will use some variant of ASCII or its superior successive format. And so in capital A, when you hit it on your keyboard, gets translated into a 65, and then your computer picks it up. A capital D is translated to a 68. A capital H is translated to a 72, and so on. Remember when I made it a period? Well, I think I did a period. That's equal to a 46. We could write something that would print this little chart out. We could start our counter at 32 and go all the way out to 118 or something like that. Let's see what's over there. Yeah, all the way down to like 126. Let's do that. Let's go from 32 all the way down to 126. So we're going to write a little loop that prints out all the characters. We're going to write another while loop. We already have a CH, and we have an I variable. Let's set I equal to 32. And then let's write while I is less than 126. How about less than or equal to? The reason I'm skipping 127 is because it says DEL. It might be interesting to see what that would display, but I don't think it's going to be a visible character. So while I is less than or equal to 126, we're going to see out arrow, arrow, I, arrow, arrow, quote, space, equals, end quote, arrow, arrow. And I'm going to convert this to a character. I could do it the Python way with a char function and put an I in there. Char parentheses I close parentheses NDL. I could have also put the parentheses around the word care. You have the three syntaxes to choose from. The dynamic cast one that we saw is the most C++ way of doing it. Alrighty, so I'm going to run it now. Oops, what have I done wrong here? I definitely have done something wrong. If I run it, you'll see what it's doing. Why is it doing that?
You didn't have it stop.
Yeah, and the reason it's never stopping is I never changed the value of the loop control variable. Now we haven't talked about loops yet, but I++. I'm going to throw that in there so that it'll be incrementing as it runs along. And there it goes. It printed out our little ASCII chart. So a 32 is a space, a 33 is an exclamation point, and so on, all the way down to 65 is an A. And if we keep going, a lowercase a is a 97. And so a distinction you can make is that the lowercase letter is 32 greater than the uppercase version. So if a uppercase P is 80, then 80 plus 32 is 112. So the lowercase p ought to be 112. Now we may talk more about ASCII at a future point, specifically when we start talking about hexadecimal and how strings are saved in computer memory. But that's just an example of showing how to cast things. This syntax works. I'm going to comment out. I'm going to put some extra syntaxes. This one works where we use the parentheses there. That works just as well. Or you can use this one where you use that dynamic cast syntax. Dynamic underscore cast angle brace, and then you specify the type. CHAR, and you close the type. All right. Do I have a preference? Well, when I learned programming, that's what I learned first. The Python folks might learn this one first, although you usually used int or float. This is considered the modern awesome way of doing it, so if you want to impress your friends, do it that way. All right. So C-style and pre-standard type cast expressions. The C-style cast is when you prefix the variable with the data type like that. And I learned C programming before I learned C++, so I learned that syntax. And then the pre-standard C++ cast. For some reason, a guy who invented C++, Bjorn Strustrup, decided that he wasn't going to accept this syntax, and he was going to modify it to look like that, which I'm sure there was a reason for it. But then when C++ was standardized, they came out with static cast. Now, did I make a serious error, and in my example I put dynamic cast? That would work, but the keyword that is introduced in the book is static cast. They do slightly different things, and I'm sorry that I used the term dynamic cast. Yeah, here I gave you the correct example. We could prove that it worked. I'm going to uncomment that one, change it back to dynamic cast just to watch it work. Ooh, no, it doesn't work. See there? Alrighty. Definitely would have to be static cast, and I apologize for using the term dynamic cast, which is a way of converting between objects of two different classes. We're not talking about classes yet. By the way, in Java, there's no difference. If you're going to cast between two data types, you just use the same keyword and use the same syntax. You use this syntax right there. That's the Java way of doing it. None of these variants work in that language. So both are still supported in C++, although static cast is preferred. Why don't we Google up why that might be the case? Just for my own curiosity. Why is static underscore cast better? I type that in. It takes me to stackoverflow.com, which is the font of all knowledge. The main reason is that the classic cast makes no distinguish between what we call, oh, forget it. Feel free to read that on your own time. Multiple assignment and combined assignment. Multiple assignment just means that you do something like this. X is equal to Y is equal to Z is equal to 5. And these have right associativity, which means that they are evaluated from right to left. The assignment operator goes from right to left. So the 5 gets copied into Z, then that result is copied into Y, that result is copied into X, and so they all wind up being 5. Now I wouldn't call this a combined assignment. To me, well, I guess I won't argue with it. Sum equals sum plus 1. It's performing a calculation and it's storing its result back into sum. There are improved syntaxes for that. Sum plus plus being the preferred C++ way of doing it. You Python programmers learned sum plus equals 1. So here we go. The combined assignment operators provide a shortcut. And there's several of them. For every binary operator, every mathematical operator, there's a compound version of it. So to do addition, if you're going to do sum equals sum plus 1, you can do sum plus equals 1. If you're doing subtraction, you would make it minus equals. If you're doing multiplication, it'd be star equals. Division would be slash equals. And modulus would be percent equals. So let's play with that a little bit. We have our handy dandy int called I. Let's set it equal to 100. Now let's add 10 to it. I plus equals 10. At that point, it's going to equal 110. If we printed it out, we would see that. CI error NDL. Now let's subtract 20 from it. I minus equals 20. And then I'm just going to copy that line right there and paste it. Now let's multiply it. I times equals 3. Let's print it out. And I divided equal by 4. And then print it out. So this just means take the value of I, add 10 to it, and store it back into I. Take the value of I, subtract 20 from it, and store it back into I. So these are compound assignment operators, or shortcut compound operators for short. I guess I'll use the whole term, combined assignment operators. Okay, fine. This textbook uses a slightly different term, so we're going to call these the combined assignment operators. Combined assignment operators, which some texts call compound operators. Plus equals, minus equals, multiply equals, divide equals, and mod equals. And their equivalents. This is the same as, I'm not going to even, you understand. So example, x plus equals 10 is the same as x equals x plus 10. All right, and so after all of our combined assignments, 110, 90, 270, 67. Formatting your output. I'm going to skip this section. What this section shows us is some useful stuff. Like, what if you wanted all your numbers to have 2 decimal points displayed? Well, why would you want that? Because we like seeing things expressed in dollars and cents, right? Instead of seeing $3.4, we'd rather say 3.40. And so this would be useful to us in order to do that. But I don't think that it's as important as some of the topics that we're going to be hitting soon. So we're making an executive decision to skip that stuff. I should probably modify the quizzes to match. Working with characters and string objects. See, this is way more important. Why do I say that? Because the way that C++ supports formatted output is so profoundly different than the way that you did it in Python or Java or JavaScript or in C# that, anyways. Okay, characters and string objects. A string is just a sequence of characters. So if you use CIN with the arrow to input strings, you can get a problem. Why? Because it passes over and ignores any leading white space characters. And then it ends at the first white space character. So if you say, please enter name, and they type in Donald space Trump, well, the only thing that's going to be read is Donald. It's going to stop at that space. And then that word Trump is going to be left hanging out to cause problems. So like this, cout, what is your name? Parentheses, or not parentheses, question mark. End quote, semicolon. Now let's create a string variable called name, and let's let them type in the name. And now let's ask them for their age. Or even what month were you born in? What is your birth month? Question mark, space, end quote, semicolon. Now let's make a variable called month and read into it. String month, CIN arrow month. Now let's write that data, let's echo that data back. Cout arrow, their name, arrow, was, space, was born in, space, end quote, arrow, month, arrow, ENDL. All right, what is your name? My name is Donald Trump. What is your birth month? And it didn't even let me finish entering my data. Instead it says Donald was born in Trump. All right, what happened? I entered 2 tokens here. Tokens are data separated by spaces. The CIN read only up to the first space, stored that in the first variable. Trump was left in the buffer. And so when we tried to read something into the second variable, it put Trump in there. It decided that the birth month was Trump. And so when we printed it out, it said Donald was born in Trump. So if you need to read data in, that includes spaces. You can't just use arrow like that. Instead, you use a function called GetLine. So we should replace this code here to use GetLines. I'm going to comment this out, CIN arrow name, so that I can fill it with the correct syntax. Let me make sure I get this syntax correct. Okay. GetLine, parentheses, CIN, comma, name. And then I'm going to comment out this one as well. The CIN error month, I'm going to replace it with a similar syntax. GetLine, parentheses, CIN, comma, month, into parentheses, semicolon. Now what GetLine does is it doesn't just stop at the first space. It reads in everything until the enter key is hit. That way, if we type in first and last name, or first and middle and last name, or 7 names, whatever, then all of that will be stored in the name variable. Nothing will be left in the buffer. And if they happen to enter, 2 words for their birth month, then that would be stored in the month variable as well. So what is your name? Donald Trump. What is your birth month? June. And it says Donald Trump was born in June. It's working now. So if your data input needs to allow spaces, then you're not just going to use arrow. You're going to use getLine. And if we take this apart, getLine is a function that is reading from this stream. Why is that important? Because a stream could also be a file. We could be reading from a file rather than reading from the keyboard, and the same function will work. It would be getLine, parentheses, but instead of CIN, it would be something else. It'd be a file stream variable. Anybody need typo correction? Okay, pardon me?
Whenever I do it, instead of typing that, it says June was born. Oh, wait, that's
Oh, okay, yeah, because you reuse the name variable. Yep. So what happened there is just you saved some time, you copied, you pasted it, and then when we ran it, it said June was born in June, or born in nothing. All right, so good catch. You figured that out before I looked. Now there's a problem with getLine. It can get to the point where it gets confused and you need to clear the buffer before the next time you try to read some input. We'll talk about, I think I mentioned that last time. You can get to the point where if you enter too much data, okay, we'll get to that point. To read a single character, you can use CIN like that. Like we've defined a char variable, and we say strike any key to continue, and then we do that, and that doesn't really work. We could give it a shot. We might put it into our code and see if it works. Instead, you use CIN.get. .get gets a single character. Now, frankly, I wonder why. If they have a getLine function, why didn't they make one called getChar, right, that did that? To make it symmetrical with getLine. But I didn't invent the language, and they are way smarter than me. So CIN.get will get a single character. Let's play with that and let's see if we can do something with it. So let's do cout, hit a key. ENDL. And then CIN.get and let's store the result of that in CH, like that. And let's print it out the same way that we were printing stuff out earlier. Cout, arrow, you pressed, space, end quote, arrow, CH, arrow. And I'm going to put an equal sign there so that we can print out the ASCII value of it. So, quote, space, equal sign, space, quote, arrow. Now, I'm going to hit enter on this. It's going to go to the next line, but that's just because I have a large font. Followed by the integer version of CH, followed by ENDL. Now we're going to get to the point where we're asking for so much input and we keep testing it and we have to type stuff in every time that it gets tedious. Let me test it out and then I'll close the window. What is your name? Bob. What is your birth month? June. Bob was born in June. Hit a key, P, and I hit enter, and it says you pressed P. It's equal to 112. The reason we did that is because what would have happened if they'd wanted to hit space as their character? Bob, June, space, enter. That would not have worked if we just used CIN arrow arrow. Because why? Because it ignores spaces. This let us hit spaces. Now it should say hit a key and then enter. What happens if we hit enter without entering a key? Bob, June. So we hit a key, we press something, it was equal to 10. Carriage return. If we look in the ASCII, we can find out that that's probably equal to a line feed. Where's our ASCII table? What is a 10? A 10 is known as a line feed or new line. That's what gets sent every time you hit the enter key. So if you want to read in a single character, you can call .get. If you want to read in data that's got spaces in it, you use GetLine. I'll make those comments. So if you want to read a string that includes spaces, use GetLine. Example, GetLine parentheses CIN comma variable. If you want to read a single character, use CIN.get. Example, CIN or CH, our character, is equal to CIN.get. See where we're going with this. And what I mean by that is what our next homework assignment is going to be. A lecture towards that. That's Java. We're not learning Java. Bless you. So this is going to be our homework assignment. Write a compound interest calculator. Fortunately, there's a formula for that. Now I've tried writing my own compound interest calculator that used a loop, like to calculate monthly interest, and for some reason it did not give the same answers as formula. But this is a very well-known documented formula, so I trust it more than my own programming. So what are we going to do? We're going to ask the user for a couple of values. We're going to ask for the initial deposit. We're going to ask them for the rate, expressed as a fraction, for example, 0.06, rather than typing as 6%. And then the number of years. Now we're making an assumption here, which is that the money is compounded on a monthly basis. And so 12 is hard-coded here and here. If you wanted to make your program more flexible, you could ask how many times a year you wanted to compound it, and you would put that in another variable, and you would put that into your expression. But anyways, this is the formula. The deposit times the power of this value to that value. I can't explain the formula to you, but that's what it is. And then display the final amount. To earn full credit, add good comments to your code. What do I mean by that? Document up at the top that it's a compound interest calculator. And then when you ask for input, call that the input section. And then in the calculation, document that you're doing a calculation of compound interest. And then in the output section, put a comment to the effect that you are performing output, or that you are displaying the result. So supposedly with a deposit of 1,000 and 5% interest, 0.05 for 10 years, you wind up with a balance of 1647.01. See if your program equals that. If not, maybe there was a flaw in my expression. You can Google it up, see if you find a correction to make. So this is actually a fairly short program if you know how to do output and input. And I think we do. This doesn't do anything complicated like using GetLine or CIN.get. You're just going to display a question, what is the initial deposit, and you're going to let them store that. Now what kind of data type should initial deposit be?
Probably a float.
It ought to be a float. So yeah, let's make it a double since that's our recommendation. How about interest rate? Again, it's going to have to be a float, right? So make that a double as well. And how about years? Well, what if they want to enter 1.5? So I think I would make all three of those variables doubles. I think you would find that if you made them ints, then bad things would happen. It would display definitely wrong answers. Okay. We're at a point, right, where we know how to do all this already. Is this a good working assignment? Some of y'all are not nodding your head yes. I hope it is. I hope it is. Because I haven't lectured today specifically for asking questions and then displaying the results. And we could do that if we wanted to. We have a few more minutes. What's another famous formula? Force is equal to mass times acceleration. Or E is equal to mc squared. All right, so we're going to write a little program to do some calculation. We're going to just tack it onto here. We want to calculate E is equal to mc to the power of 2, or like that. Now there is no exponent operator, so we cannot do that. So we're going to ask for input. Let's declare our variables first. Double E, comma, M, comma, C. Input E and M. Now C is a constant, if I remember from physics. This is just Einstein's relativity equation for the conversion of mass to energy, which is what happens when you do in a nuclear bomb. Is some of the atoms are converted from mass to energy. Okay, so let's write a message out, C out, enter the mass, or quote, enter the mass, colon, end quote. And I made the arrows go the wrong way. So it should be C out less than less than. Now what are the units of EMC squared? I'm going to Google them up real fast. Kilograms. Alrighty. So enter the mass of kilograms, like that. And let's read that result into E. Now we're not actually inputting E. That was my mistake. That's the results of the calculation. So I'm going to change my comment to input E, parentheses, mass, in kilograms. Now I'm going to need the value of C. It's a constant. I believe it's the speed of light. I'm going to go and Google up what that is. Come on. Don't waste my time. Oh, you gotta be kidding me. Alrighty. Thanks for hiding behind a paywall. It's 3.0 times. Yeah, there he is. We're just going to roll with 300,000 kilometers per second. But is that what we want? And E is equal to mc squared?
That's 3 times 10 to the 8.
Yeah. That's meters per second. So 3 exponent 8. Yeah. Okay. So C equals speed of light in meters per second. Put that comment there, and it's equal to 3.0 exponent 8. Now we can do our calculation. Perform calculation. Energy is equal to mass times, now we need to take the square of C. Easiest way just would be C times C. Or if you want to use the POW function, you could do that. I'm going to change it to do that. E is equal to m star POW C to the power comma 2, like that. Output result. C out. That mass produces space, quote, arrow, arrow, E,
Your M isn't defined.
just a sec, before my brain forgets what I'm typing here. C out, E, arrow, arrow, joules, backslash n, end quote, semicolon. Okay, pardon me, what I do wrong?
Your M isn't defined. Your CN is for E, not M.
Yeah, that's dumb. We're not reading into E. I even made that comment, but I forgot to correct it. Into the mass of kilograms. Okay, there. Now what I should do is when I declare all this stuff, I should comment what they are. So I'm going to do that. I'm going to rewrite this double EMC up here. I'm going to say E equals joules produced, and then double M, semicolon, M equals mass in kilograms, and then double C, C equals speed of light in meters per second. In which case I can get rid of this comment. I could change this comment to input mass. We've already defined what units it is. When I declared C, I could have given it a value right off the bat rather than wait until we got down here. I'm going to leave that alone though. Perform the calculation. E is equal to m star pow C2, output result. Let's see if it works. I mean, not that I'm going to know if the answer is correct or not. What is your name? My name is Bob. I was born in June. Hit a key. Enter. Enter the mass in kilograms. Okay. I want to find out what 1 gram is converted to joules according to E is equal to mc squared. So I'm going to type in 0.001 because that's 1 gram. And that produces 9 to the exponent 13 joules, which is a lot of energy. Doesn't seem large enough. I guess it's a lot though, right? 9 followed by 13 zeros. That's a lot of energy just from 1 gram. How about a kilogram? Run it again. We have a kilogram of uranium and a perfect conversion. So, Bob, June, hit a key, 1 kilogram. All right. However many billion joules that is. All right. So, in our notes, you will now find an example of getting input and then displaying output. But your program is going to need to read in 3 variables, not just 1, or at least 2. Yeah, we're going to ask for the initial deposit, we're going to ask for R, and we're going to ask for T, number of years. And if you feel like modifying it so that it'll compound something other than just 12 times a year, you could ask for that as well. All right. Any questions? Anybody need typo correction? Well, that's no fun. Everybody typed it incorrectly? All right. Let's make a Dropbox.